Hi there, I am Raluca Gaina, PhD student from Queen Mary University of London. And this is TAG, an AI framework built around tabletop games. This is an ongoing project started during an internal game AI hack, which continues to be developed and attract contributions from many more researchers and students as I speak. The TAG project is all about tabletop games. With this term, we mean any sort of analog game that can be played on a physical surface. Examples include, but are not limited to, board games, card games, dice games, role-playing games, and other pen and paper games. And more specifically, we're looking at modern tabletop games. This term is harder to define, as the type of games we are interested in were played even in ancient times, so not exactly modern, but in this context we refer to those games that are of high complexity. They contain many different types of components, combining cards and dice, for example, many rules and types of interactions between many players. A lot of these games also include partial observability by hiding parts of the board or some players' hands, or by placing randomly shuffled decks or cards face down on the table. Players often take on different roles within the game, and each game has a series of parameters that control its flow and balance, such as the number of cards in a player's hand, or the number of events that take place at a specific point in time. These games often feature unique game state representations due to their complex collections of game pieces, may include both cooperative and competitive aspects between players or between players and the game, and they often have very large action spaces. All of these make them very interesting problems for diverse artificial intelligence methods. We've seen the growth of AI techniques closely linked to traditional board games since its very beginnings, with artificial players becoming proficient at chess, Othello, and more recently Go. But research has also looked into other types of tabletop games too. There have been several AI agents playing card games or games focused on deceit and asymmetric player roles, such as The Resistance and Ultimate Werewolf. AI players have started attacking games of higher strategic complexity, such as Pandemic, or with large action spaces, such as Blood Bowl. And we've seen specific applications of statistical forward planning methods in Settlers of Catan, Risk, and Splendor. What's special or interesting to us about these cases is that statistical forward planning methods require a model of the game in order to perform simulations of what might happen in different situations. Models which can become large and slow with the more complex the game is, yet allow these powerful AI methods to play games to a high level of performance. And these models are also an additional programming step, which can become tedious to implement. But AI is not only used for playing these games anyway. We can see applications of AI for playtesting in Ticket Ride, meant to find bugs, balancing issues, or exploits, which usually become apparent only after extensive human playtesting. And we've seen the relationship between tabletop role-playing games and procedural content generation drawn by Matthew Gustile and others quite recently. Some of this work was brought together into commonly used frameworks featuring a collection of different games and AI players for easy benchmarking of new methods. Some of these include the General Game Playing Framework, or GGP, from all the way back in 2005, and more recently the Ludi and Regular Board Games, or RBG, frameworks. All of these describe their games in a framework-specific language. GGP uses the game description language, which describes the state of a game as a series of facts and the game mechanics as logical rules. Ludi uses a series of ludims, or game logic units, which together make up rules or state representations. And RPG uses regular expressions for improved efficiency. At the other end of the spectrum, there are freeform frameworks which allow developers to build games with intuitive tools or complete programmatic control, such as the Tabletop Simulator and OpenSpiel. In these cases, adding games become much simpler, as users do not have to learn a framework-specific language and all of its intricacies. And even more, the limits which might exist in the framework's description language can be overcome here, as almost anything becomes possible within the limits of the user's technical abilities, of course. We take the best of these approaches forward to build our own framework, with three main contributions targeted. First, we bring into focus the challenges brought by modern tabletop games for AI methods. Second, we promote research into general artificial intelligence by providing a common API for games and AI players allowing artificial players to try to solve an ever-increasing collection of problems. And third, we provide features to facilitate the development of new games and AI players under the same common platform, and invite community contribution to drive research forward. But let's dive a bit deeper into what the framework actually does. TAG is built in Java, taking advantage of the execution speed of this language, and several AI players are already available and provided with the code. We do not use a game description language, everything is pure code, aiming to speed up development and execution, as well as lower the barrier of entry for new users. The core of the framework is made up of several abstract classes, providing generic functionality and a simple-to-follow skeleton for implementing both the games and the AI players. Several classes can further make use of additional interfaces to allow compatibility with other systems included, such as the automatic optimization of parameters or custom observations. We provide several ready-made rules, actions, and components which are common across a wide variety of games, all of which are easily extendable. We include a graphical user interface compatible with any game, allowing to run it as soon as the two main skeleton classes are created, the game state and the form model. Tag further includes a fully functioning game loop, game tagging or categorization for easy filtering through the games collection, as well as game analysis. We currently have 8 games implemented and several general AI players compatible with all of the games, although compatibility does not equal proficiency in all cases, as we'll see a bit later. We use several concepts common in tabletop games to define the core of a game. Actions are things players can do in the game. Rules are things that the game does, outside of a player's action. Turn orders define the order in which the players are going to be asked for actions. Game phases are time frames in which specific rules apply or the players have specific actions available. And each game is made up of several components or game pieces, which is what actions and rules modify to change the state of the game. Components currently supported include tokens, cards, dice, counters, grid and graph boards, all with different properties and functions associated. We can also group these into collections. Decks are ordered lists of components, and areas are maps, mapping from the component ID to the component object itself. Both areas and decks are considered components themselves and can be stacked. For example, an area may contain several decks. In order for a game to be created, 2 main classes are required, a game state and a form model. The game state is a container class made up of game components and any other variables that can be used to speed up execution. A game state describes a moment in time and defines component access methods and optionally a scoring function to be used by the AI players. A game state can be copied, and the AI players receive such a copy reduced to only include the information they can actually observe at the time. The form model contains the logic of the game, including all the rules that modify a given game state. It sets up the initial state of the game, decides which actions are available for the players, applies players' actions and game rules in order to advance the game state, and checks for any end-of-game conditions. The form model is available for AI players for game simulations. Currently, we have 8 games implemented in the framework, starting from very simple instances such as tic-tac-toe and dots and boxes, to more complex games like Pandemic and Colt Express. We also have several games currently in progress, including Descent, Carcassonne, and Settlers of Catan, the last of which should be ready very soon. And to actually play these games, you can do so as human players in 2 ways. Via the console, which would print out the game state and ask for the index of the next action out of the suggested possibilities, or via the graphical user interface, which by default includes buttons to all of the possible actions and dragging components on the screen, but also include customized interactions such as selecting specific game pieces for filtered action lists. Additionally, we have 4 artificial players that can be run with any game. Random takes a random action out of all possible. One step look ahead, or OSLA, greedily selects the action which leads to the next best state. The rolling horizon evolutionary algorithm, or RHEA, evolves a sequence of actions and chooses the first action of the best sequence to execute at the end. And Monte Carlo Tree Search, or MCTS, builds and searches the game tree for the next best move. OSLAR and MCTS all use the form model to simulate possible future scenarios and an evaluation function to evaluate the game state. We've tested our agents on the current collection of games. For Tic-Tac-Toe, which is a two-player only game, we've run a round-robin tournament where each agent played 100 times against all other agents. In Pandemic, we've run teams of the same agent type 100 times each. For all other games, we've run 100 four-player games with one instance of each player. For the search-based algorithms, we used a budget of 4,000 for model simulations at each decision-making game tick. Results generally indicated MCTS to be the best agent, with the highest win rate in 5 out of 7 competitive games, that's excluding Pandemic, and an overall win rate of 41% in these games. OSLA also appears to beat Rhea in some of the games, which is potentially due to the large uncertainty built up in the Rhea's rigid sequences of actions, as opposed to the more flexible game trees of MCTS, with the greedy approach appearing to be preferable in some games, especially those simple enough or with a heuristic function accurate enough, such as Tic-Tac-Toe. However, we do observe Rhea to clearly dominate all other agents in dots and boxes, a game not included in the earlier paper publication but added for this presentation. This is an interesting case to be analyzed in more detail. We also note that no agent is able to win in Pandemic. Stronger heuristics and better analysis, such as the distance from the winning game states for each AI team, could lead to improved performance or show interesting insights into the agent's behaviors and abilities. Additionally, Uno and Colt express a very close performance for all players, including random. This highlights the difficulty of the problems proposed, as well as the importance of the heuristics chosen for the game, as some features of the game state may prove deceiving, such as having more cards in hand in Uno. However, it is worth noting that the search methods presented were tested in their vanilla form, but they benefit from ample literature and large parameter spaces which can be tuned for increased performance. Lastly, I want to take a look at the future and the opportunities for research opened up through this project. There are lots more details in the paper and I don't have time to go through all of them in detail, but I want to highlight two things here. The first is role-playing games. This is a very difficult challenge as it goes beyond tactics and playing the correct actions towards even finding which actions are possible or make sense in a situation, and building a consistent, engaging story with the other players. Plus, these games often feature a dungeon master or game master whose job is not to win necessarily, but to give the other players an interesting experience. How would an AI even go about that? The ongoing implementation of Descent in our framework aims to be a step in this direction. And second, I'd like to briefly highlight that the framework offers functionality for easily optimizing parameters of both AI players and games. If you're looking for a better balanced version of your favorite game, TAG could put that together. And if you've zoned out through most of this presentation, please take these three things away. First, that Tabletop Games presents so many exciting opportunities for research. Go play one and think how an AI method would do something that's happening in that game. Second, that I've been talking about our TAG project, which is all about building a collection of tabletop games and AI players able to play them all. And third, do check it out yourself. Download the GitHub repository, have a play, and give us feedback or even start implementing your favorite game today. Thank you very much for listening. If you'd like, you can read more about TAG, find more details about our Game AI group at Queen Mary University of London, and all of the exciting things that we get up to, or get in touch with me through the links on the screen. Have a great rest of the day.